Here's an interesting example of a hypothesis test used for quality control. A lumber company makes boards, and they don't want to test or measure every board to see if they're making them to the right specifications, so instead they'll make a sample of 18 boards and measure those 18 boards to see if their machine is out of calibration or if they need to adjust it so that they can not be making them that are too long or too short, which obviously would have implications. So the board themselves are supposed to be 2756 millimeters tall. They sampled 18 and found that the mean of the 18 was 2757.4 millimeters, and there was a standard deviation of 9.0. The level of significance is 0.1, and we want to determine if they are too long or too short. To run this hypothesis test, we follow the same 4 steps. First, determine the null and alternative hypothesis. Null hypothesis, the boards are assumed to be 2756 millimeters. Alternative hypothesis, perhaps they are not 2756.0 millimeters, and they could be error on either side, so it's a two-tailed test. Evidence at the 0.1 level, so alpha equals 0.1. Second, we need to create the test statistic, so that makes us ask, should we do a T or a Z test statistic? Remember, we have one basic criteria here. Is sigma known or unknown? We read through here, there is the word standard deviation. Is it for a population or not? Reading the sentence, it says a sample of 18 is made with a mean of 2757.4. So that mean refers to the sample, and with a standard deviation, which also refers to the sample of 18. So sigma here, the population standard deviation, is unknown. When that is the case, the T distribution is appropriate. That means that our T test statistic will be x bar minus the mean divided by s divided by the square root of the sample size. We can do this by hand. X bar, sample mean, was 2757.4. Assumed mean 2756.0 divided by the standard deviation of 9 millimeters divided by the square root of the sample size, which is 18. This works out to be 0.65996, or about 0.6570 to not 70. Or about 0.660 to 3 decimal places. The next step is to cook up the p-value. What is the p-value for this test statistic of t equals 0.660? What's the probability that we get a board that's too long or too short? Now remember, this is a two-tailed test, so here we have one test statistic, 0.660. We care if it's too long, but also because it's a two-tailed test, we want to consider the probability of a board being too short. So we have the probability that we're less than negative 0.660 or greater than positive 0.660. To use technology for this, we could use this TCDF distribution with a minimum of 0.660, a maximum of 10, and a degrees of freedom of how many? Sample size is 18, degrees of freedom is 17. That would give us the area here to the right of 0.660, and then we would multiply by 2, and multiply by 2 because it's a two-tailed test, that we care about where that probability is in either the tail to the right or the tail to the left. That value is the distribution menu, TCDF. Lower 0.660, upper is an ambiguous large number. Anything bigger than 5 will do the trick. 10, 100,000, million. degrees of freedom are 17. So that's 0.2590 and multiply it by 2. Because of the two-tailed test, we get a p-value of 0.51809, or about 0.5181 to 4 decimal places. Alternatively, if we don't just do the CDF, we could run the whole test in the calculator, run a t-test. Remember, that is in the stat menu, tests, number 2, t-test. We will input statistics. We have summary statistics from the sample. The null hypothesis was 2,756.0. Sample mean was 2,757.4. Sample standard deviation was 9.0. And the sample size was 18. We're testing two tails, that the alternative hypothesis is not equal to the null hypothesis. This verifies for us the p-value that we found before with the CDF, 0.5181 to 4 decimal places. Then next we just have to decide the test. What's going on with this p-value? Is the p-value low, less than alpha, or not? If it is less than alpha, reject. If it's not less than alpha, fail to reject. Alpha is 0.1, p-value is 0.5.